Okay, thank you. So yes, after the great background and introduction to microlensing that we had yesterday, what I want to talk today is to tell you the story of the discoveries of microlensing planets. And as you can see, even from the artist impression of some of our systems, there is a large diversity in the planetary systems that we detect with microlensing. Now, the story of the planet discovery is also in some way the story of the microlensing field, and as it evolves through different stages of surveys and follow-up, and I'll try to show it in my talk. Now, I think it's very important, especially in this kind of a school, not to start with the discoveries, but to start with what I can call like the failed discoveries. The event that before the first microlensing planet discovery, we thought that it was a planet, but it ended up not to be such a planet. So it's quite remarkable that the very first microlensing event ever published could not be explained by a single lens. You can see here there are two clear deviating points. Now, a year after the discovery paper, Dominic and Hirschfeld showed that a binary lens can explain this light curve. 2 years later, they showed, as we learned yesterday, that there is a large degeneracy between the solutions. And actually, one of those degenerate solutions suggested that it might be a Jupiter mass planet. First discovery before any other planet. Now, since there have been a few claims for planetary detections, either with a weak signal, okay, so yes, the planetary signal might fit this light curve better, but it's hard to claim a detection. Or again, sparse, just one deviating point, maybe two deviating points that many models can take this into account. Now, maybe the best planetary candidate before the first discovery is Macho 9741. As you can see here, there is two clear anomalies, not with one point, with several points. And not only that it was claimed to be the first microlensing planet, but it was the first circumpolar planet overall in all planet detections. You can see here there is, sorry, I gave you the answer. So there is a secondary binary of a secondary and a primary and a planet that need to explain that. But a year later, a different group with a different data set shows that this can be explained by just a binary lens rotating. And a matter of fact, a few years ago, Zhang et al. Combined the two data sets and shows that indeed a binary rotating fit is favored. Now we need to remember all of this in order to learn from our mistake. And this wasn't the last mistake. Even after the first discoveries, we had Dave mentioned one of them yesterday, acclaimed planets that turn out to be actually a binary and a binary source. So we need to be very careful. Microlensing modeling is very, very difficult. So now we're getting to the first microlensing planet. It's an event from 2003. What we can see here is that there is a clear anomaly and that it lasts long enough that we have a good sampling of the event. Now, we need to think, why is that? Now, it's only Survey, Ogle and Moa, only the main Survey group covered this event, no other team. And how could they do that? Well, first of all, this is quite a long event. Its time scale is 60 days, which a typical time scale that we learned yesterday is about 20 to 30 days. It's a Jupiter mass ratio planet with Q 10 to the minus 3, but as you can see here from the caustic, the location of the planet is close to the Einstein ring, causing a resonant caustic, so a large caustic. So we have a long time scale event with a large caustic. The anomaly lasted 7 days. So the survey-only data was sufficient to capture this anomaly. And the next talk after me is by JP. We'll talk about high-resolution imaging that turns out to be a very important tool when we don't have all the higher order effect to break all the degeneracy in microlensing model. And actually, Bennett et al. In 2006 used HST observation to identify the host star and found that this is a 3 Jupiter mass planet around a K dwarf at about 4 AU. Quite a typical Microlensing plant detection. Now, it was realized actually before this event that a different strategy needs to be taken in order to capture this small deviation and to have a good sampling of anomalies so we can claim detections. And this is what we call the alert and follow-up mode. So the main survey group, Ogle and Moa, detect events, they alert them to the community, and we have some criteria on which events we select or not, but it doesn't really matter. Some events are followed by a network of follow-up telescope to cover, hopefully capturing anomalies. And so the second Microlensing event is exactly like that. It's a high magnification event. You can see it starts at 19 magnitude and goes up to almost 15 magnitude. And over the peak, we have the double-horned feature suggesting that it's a planet. We see that there are a lot of other groups other than Ogle capturing the anomaly over the peak. So this time it's a central caustic. We have what we know from yesterday, the white closed degeneracy, but nevertheless it's again about 10 to the minus 3 mass ratio, suggesting that this is a planet. This event again, quite a long time scale event, 17 days. So although it's a central caustic and we learned that it's the smallest caustic, still we have almost 3 days of an anomaly, so we capture all the features. And again, HST observations were taken, and moreover, Subo showed that actually Microlensing parallax needs to take into account the annual parallax, and only combining HST and reanalyzing the event, he showed that it's a super Jupiter around an M dwarf of 0.46 M dwarf, either at 2 AU or 3.5 AU. Now we're starting to get into the physics that Microlensing can probe, or the plant formation regimes that we can understand. And why is that? Well, it's a super Jupiter around an M dwarf. And it's hard to create such planets according to core accretion models. Also, this instability suggests that we can create such massive planets around M dwarf, but they should be further out. So Microlensing starts to have a key in constraining plant formation. Now I'll skip, later I'll continue with the chronological detections, but I'll skip to the end of all Microlensing discoveries until now, or at least the public ones. 20% out of the Microlensing planet detections are of super Jupiters around M dwarf. Okay? It's a large fraction. Now we need to remember, this is not easy to do the statistics. M dwarfs are the most common lenses. A super Jupiter will be the easiest to detect around such an M dwarf. So there are detection efficiency and completeness things that we need to take into account before we do the statistics, and Daisuke and others will talk about the statistics after me. But what we can probably say that at least super Jupiters around M dwarf are not rare. How common are they? It's a different question, but it's not a rare phenomenon. Otherwise, we wouldn't detect it in 20% of the events. Now, the third event is of another feature. So this time, it's a low magnification event with an anomaly at the wings. And as Scott told you yesterday, this time it's a planetary caustic. So we had 3 first Microlensing events, and we covered the 3 possible topologies. That's it. We're done. Okay, now we need to detect more. But this time, it's actually a short time scale event. The time scale is only 10 or 11 days. And the anomaly is very short, half a day or even less, suggesting of a low mass ratio planet. And a matter of fact, this turned out to be the lowest mass planet at the time, except pulsars, a 5.5 Earth mass planet. Now, this time we didn't have HST, a follow-up imaging of any AO, so what we did is something that we usually do, which is Bayesian analysis. What we do, we take a galactic model and we say, okay, for a T of 11 days to that direction, what's the probability of the host mass? Once you have the host mass in a Bayesian way, you can, from the mass ratio, derive the planet mass. Now, the fourth planet is quite similar to the second one, high magnification, anomaly over the peak, captured quite nicely by follow-up group. But what's really exciting about this event, that this is the only event so far that with follow-up observation we could actually detect and separate the source and the lens. So 6.5 years after the event, it was observed by HST. There is some suggestion that the source and the lens are separated. You actually need to have 2 PSF in order to model this image. But 2 years later, Batista used a Keck observation to clearly resolve the lens and the source. Actually, the lens is the brighter one in this event. Now, with this, you can fully solve the physical properties of the system. And what they found that it's another mini Neptune, if you would like, planet. Now, although we had to have the follow-up to fully constrain the physical properties, but also just from the discovery we had, they had a good understanding of what kind of planet it can be. And so this was the first time that they could start talking about something about the statistics. Well, 4 planets, but something about the statistic of microlensing detection. So in this plot, what I show here is the 7 major axes of all planets and the mass of the planet. You have in black the RV, blue transit, and the purple ones are microlensing. You can see that we have 4 planets. 2 are Jupiters or super-Jupiters, and 2 are Neptunes or mini-Neptunes. But as I told you, it's harder to detect those mini-Neptunes. So just by the fact that you have the same number per DEX, and you have the detection efficiency, you can say or suggest that Neptune-like planets are common. Now again, I'll skip a few planets later to the 10th planet, which was again a mini-Neptune or a Neptune mass planet. And if this was the picture in 2006, this is the picture in 2010. So again, we have 10 planets, more or less the same number of planets per DEX, suggesting that indeed Neptunes are common. Moreover, now you can start to constrain the slope of the masses of the planets, and what they show that Neptunes are at least 3 times more common than Jupiters. But another thing that we need to remember is that the host of the planets are different for different techniques. Microlensing usually probes M stars. Other techniques which picks their stars that they look for their planets usually focus on G stars. So if we'll scale the 7 major axes to the host mass and show where the snow line, which is a very important place in planet formation scenarios, we'll see that, again, please look at the red dots, that microlensing, and the snow line here is the vertical line, microlensing probed very nicely just beyond the snow line, which is the location that we think that giant planets should form. So this is the technique to probe those planets. So what we can actually say, or what they could actually say, that Neptunes are at least 3 times more common than Jupiters beyond the snow line. Okay? So I did it in quite details for the first 4 planets. From now on, it will be a bit faster. Now, it was supposed to be a question, but since you saw this light curve yesterday, you probably know the answer. This is the 6th system discovered by microlensing. We have a lot of features here, okay, suggesting of a resonant caustic, but we actually have one feature too much, and this is feature number 4, suggesting that there is actually another lensing mass, and this was the first 2-planet system. Now, what we know from yesterday that microlensing measure very well mass ratios and separation in Einstein units. However, if you have 2 separation, you can have the ratio between them, and you don't care about the Einstein unit, the Einstein radius. So this is the parameters of the model. So we have the more massive planet, it's about 10, the mass ratio is about 10 to the minus 3. The ratio between the 2 planets is about 1 to 3, and the more massive one is closer, and it's about, its 7 major axis is about a half of the lower mass planet. Now, do you find these properties familiar? Well, you should. You live in such a system, okay? So if we look at the solar system, the massive planet Jupiter in our system is about, the mass ratio is about 10 to the minus 3. The ratio between Saturn and Jupiter is about 1 to 3. The semi-major axis ratio is about 0.5 with the more massive planet inside. So this is what we call a solar analog. Now, again, with follow-up observation, this time with Keck, the physical properties were better constrained, although already from the discovery paper, most of them were realized. The host is only half a solar mass, so everything is scaled down. The distances are half of Jupiter and half of Saturn. The planets are slightly less massive than Jupiter and Saturn, but this is what we call the solar analog. Now, I will also remind you, this is the sixth planetary system discovered by microlensing. And already the sixth one was with two planets similar to the solar system, suggesting that solar systems are quite common. But again, I'll skip to the end, and for the rest of the 40 system published so far from microlensing, there is only one additional two-planet system, an event from 2012. This time, you can see here there are way too many features to be explained by just a binary lens. Both of the planets are very close to the Einstein ring, so we have actually a four-fold degeneracy of white clothes for each of them, which you can see here from the caustics. And again, if we compare it to the solar system, the more massive one is about 10, the mass ratio is about 10 to the minus 3, similar to Jupiter, but this is the only similarity. The ratio between the more massive and the second one is not as Saturn and Jupiter, and also the aspect ratio is different. Also, with the possibilities that the more massive one is actually outside. And with follow-up observation, JP used both Keck and Subaru and found the physical properties of the system. There is still a degeneracy between two models, but both of them suggest of a Jupiter at a Jupiter distance around a sun-like star, but with a second planet nearby and less massive than Saturn. So we talk about survey only. We talk about survey and follow-up, which was the strategy that we took. And the next step is actually, I think that the person that phrased the second generation Microlensing survey phrase is Scott, where we need to do blind surveys of a large region of the sky with high cadence to detect those anomalies, because it's very hard to probe. You can relatively easily estimate that an event will be high magnification, but to find the planetary anomalies like the third planet, it's very hard, and you need a lot of resources. So instead, you just need to do a survey that can bring you all those short anomalies. Now, the first kind of this survey, it's not really a second generation survey. KMT is really a second generation survey, but it's a survey that WISE Observatory monitored a fraction of the sky where both Ogle and MOA have high cadence, so together we have almost continuous coverage. And the first event that was covered by this network is an event from 2011. And what Jennifer showed in the discovery paper is that although this event was followed by a lot of follow-up groups, the survey-only data was sufficient to fully constrain the model, suggesting that you can do that. Now, it's again a central caustic planet, and there is a strong degeneracy between the wide and closed. They're completely separate. The closed one is slightly favored. Now, why is that important? Well, this time, the follow-up observation found that this is a 5 Jupiter mass planet at either 1 AU or almost 4 AU around a G star. Now, do you find some of these properties familiar? 1 AU around a G star. So this is the first possible Microlensing planet in the habitable zone, so showing you that not just we probe beyond the snow line, but we can also probe closer in the habitable zone. It's a 5 Jupiter mass planet. You probably cannot live on that, but it shows you the strengths of microlensing. Now, another event from this that was covered by the second generation survey is an event from 2013. You can see that we have, again, a lot of feature, double horn, and a deep here. And, well, you saw this event yesterday. But I told you that we don't have any more two-planet system. It's not a two-planet system. It's the first planet in a binary system. So this is an two Earth mass planet at 1 AU around one member of an M-star pair. So it orbits the slightly lower mass planet, so I call it a secondary planet. The second event of a planet around a binary system is of a completely different kind. So you can see this event published by Radek. You have three, if you would like, separate microlensing events, almost separate. The first two are quite introducing shear to each other. But the time scale of each of these events is different. So it's not a single lens with a triple source passing by. It's actually a triple lens system. And it's found to be for Uranus mass planet about at the Uranus orbit around K-star with an M-star as a secondary. And again, this time it orbits the more massive planet, so it's the second primary planet. Now, the third planet in a binary system is an event published last year by Dave. So he already showed you this one. Although the binary model fits quite well the feature, if you look at the residuals, you clearly see a signature of another body. There were actually two possible explanations. Are a two-planet system and a circumbinary planet, but each of these explanations predicts a different flux from this system. And with HST observation, both during the event and after the event, they could rule out the two-planet system. And this time we have a circumbinary planet. So we have only three planets in a binary system: one circumsecondary, one circumprimary, and one circumbinary. Okay, just show you the diversity that Microlensing probe. Now, what they also showed in the paper that if you take this circumbinary planet, which is a 80 Earth mass planet at 3 AU around a pair of M dwarf in a very tight orbit, and you compare it to all other circumbinary planets discovered by Kepler, this is almost the only planet that is further out from the stability limit of this pair, represented by this vertical line. So also Kepler 1647 is quite like that, but Ogel 2007 349 is the most extreme case. And now with one planet you cannot say something, but again it shows you that Microlensing probe a very unique region in parameter space that other techniques just cannot do that. So the next step after the second generation is going to space. The third generation Microlensing survey will be double first. It's a dedicated Microlensing survey. We kind of try to do it with K2, but it's not quite as that. But what we can do is what Jennifer told you yesterday with the Spitzer campaign. So we monitor events. It's kind of a follow-up, if you would like, although it's a follow-up before you know anything about the event, except of that you can do it with Spitzer. And this is the first planetary deviation. Very clearly, the anomaly is shown in both ground and space, but the shift gives you quite nicely the parallax. This is from the Discovery press release. The second event, this time we don't capture the anomaly with Spitzer, but it showed quite nicely the 8 degenerate solution, both wide close because it's a central caustic, and the 4 satellite degeneracy. So we have 8 possible solutions. The physical properties are not such different from each other. So although you have a degeneracy, yes, you cannot say everything about the system, but you can constrain and say what it is. Now the third and currently the only, the last, published plan from the Spitzer campaign is an event from last year. They've already showed it to you. So this was an event that was analyzed separately by 2 groups, Ogel and Moa, which considered to be the discovery paper, as KMT, which is what I analyzed with Spitzer, KMT we couldn't have known and trigger Spitzer without Ogle and Moab, without knowing that there is an event, so it's clearly a discovery paper. But what we can see here is a very, very short anomaly, less than 3 hours. And you just can't do alert and follow-up for such short timescale events, short time anomalies. And you need a survey to do that. So it was luckily that MOA could capture it, but if it was during just after New Zealand and over South Africa, no survey could capture that. But because KMT have a global network of telescope, they could capture it either here or even later. Now, combining the short timescale, the short anomaly with the parallax information, we could find that this is an Earth-mass planet at 1 AU, but a host is not a sun-like star. It's an ultra-cool dwarf at the border between brown dwarf and M star. And this leads to another regime that Microlensing probe, and it's basically the only technique that can probe very well. So what I plot here are all planets discovered by any technique around an ultra-cool dwarf. We have 4 direct imaging discoveries. Some of the direct imaging people here wouldn't even consider them planets. You know, it's 10 Jupiter mass planet at the border of what you can say. We have the TRAPPIST-1 system by transit, but we also have 4 Microlensing planets around ultra-cool dwarf. One of which is a super Jupiter, and 3 are terrestrial planets at around 1 AU. Now, what I will also plot here as these bars is different models, but all of them are core accretion models trying to see what kind of planets you can form around M stars, ultra-cool dwarf, and where can you do that. So you can see that the average planet mass is actually below Earth mass, and it's centered around 1 AU. If I'll take the maximal planet mass from their models, it reaches more or less Earth mass. And as you can see, they probe that it will form around 1 AU. So actually, we think that this TRAPPIST-1 system probably, no one really know, but probably formed further out and migrated in some way. But it shows you that Microlensing that you know is sensitive throughout this mass range. It's not a problem for us. It's easier to detect a Saturn or a Neptune rather than an Earth. And the fact that you have this gap suggests again that maybe it tells you something about planet formation. Maybe there is actually a 2 formation mechanism of binaries that turn out to be below 13 Jupiter mass planets. So we call them planets in some definition, but in other definition, they might not be planets as we think of planets forming from a protoplanetary disk, and this Earth mass planet that probably formed like what we think from planets. So again, and this might be actually also the explanation for the super Jupiters around M dwarf. Maybe they are not really formed from a planetary disk, and then you don't have any contrast with core accretion. It's just like binaries form. Now, I won't summarize all the points that I showed, because the main thing that I want you to remember before I'll show my last slide is that the large diversity that we have in Microlensing planet discoveries, and that we have unique regimes that we can constrain planet formation. But really what I think that should be the motivation, or it's not the main, but one of the motivations that should be for people outside of this field to go into this field is this slot, which is the discovery year of a Microlensing planet as a function of number. And you can see that we're exponentially rising. So this is exactly the time to join this field. Now, there is a slight lie in this plot, because as you can see in red, the actual event here is we are slightly lagging that, but this is the time to join. So you're very welcome. Thank you. the rationale is the same. The reason that I won't answer this question, that we have a talk just about that, like not the next talk, the talk after that, and don't want to steal the Suke point. But yes, when I just highlighted what just a detection suggests, and to do the real statistic, you need to do all the detection efficiency and completeness, both of just events and anomalies, and all of this is taken into account. We have, I think, 3 or 4 such papers that does exactly that. So it's not archival data, they are all known usually within the year that the event is there, but it's either hard to model, you could see we have, I think the biggest lag is like 10 years from the discovery to actually, from the event to actual discovery. Also some political tension, but I'm not aware of, maybe other people could tell me that, like an event that, an anomaly that no one knew, and later someone took the archival data and just searched for that and find this anomaly. The modeling is actually usually the limit, not the competition. But
so there's still some in the works.
I think that there are already 6 submitted papers this year with planetary detections and more. Yes. So again, I won't tell you about that because this is because this is probably one of the main findings in the Suke analysis is that yes, it's rising, and at some stage that I won't tell you where, it starts to fall, or at least it's suggesting that it starts to fall.